2.2. The limit of a function. Definition of a limit. Suppose f of x, which is the function of x, is defined when x is near the number a. Then we write the notation: the limit of f of x as x approaches a equals L, the limit. And so this is how we say it. I just said it now. The limit of f of x as x approaches a equals L. We can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a. And so what that means, this means we have this curve. So we have a curve like that, and we have a point right here, and this points are point A. We could make our x, so this is x, right? Get closer to A, and when it gets closer, it won't equal it, but it'll give us a closer look into what the value is of our limit. And so these are alternative ways to write it and alternative ways to say the definition of a limit. Note, the function of x is not even defined when x equals a. The only thing that matters is how f is defined near a. And so let's look at these graphs right here. So we have a function here. This blue lines are function, and it's going up here, it's going up here, and so this is defined. And why is it defined? Well, let's take a look at this next graph right here. So we have this function, and then it has this opening right here, this open circle, and a solid right here, solid dot right here. So this is our point P, and so this defines right here. This point is defined. Well, in this given section of our curve, at this section of the point of our curve, right, it's not defined. And so here's our limit. Our limit's approaching over here from the left side and the right side, but it's not defined right here. So it's defined on P, but it's not defined right here on the curve. And so that's why it says it's not even defined when x equals a, right? The function is not even defined when x equals a. So this is our function f of x, right? So it's not defined right here, because right here, this is a, right? This is the point A we're looking at for our limit. So I'll write out the limit right here so you guys can see. What's the limit say? X approaching a. Right, so that's our limit right here. A right here, and this continuous, not even continuous, this function here, it's going right here, but it's not defined because it's open. Alright, so let's look at the next one. So now we have this function here, this curve, and like this one, it doesn't have P though. It's not defined. Not because it's P's defined, right? But we don't have a solid point where it's defined at. So at this given section, let's say 2, right? It's not defined. Well, in this given section 2, P is defined. Example 1. Guess the value of the limit of the function of x, which is x minus 1 divided by x squared minus 1, as x approaches 1. Alright, so we know that the limit is not defined when x equals 1, because what happens when x squared, when 1 times squared? That's 1, right? 1 minus 1, that's 0. 1 minus 1 on top of 0, so we know it's not defined. because this means it's undefined, right? But what happens if we make a chart and we start plugging in numbers into our calculator? Alright, so we ended up putting numbers into our calculator, and so what's happening here, this is x less than 1, this is x greater than 1, so we're putting numbers and they're getting close to 1. So what's happening is it's getting close to a certain number, and that number is, if you take a look right here, it's 0.5. So example 2, estimate the value of the limit of the function f of x equals the square root of t squared plus 9 minus 3 divided by t squared as t approaches 0. Alright, so the first thing we need to do is we need to plug in numbers for our given limit right here. Alright, so I plugged in some numbers into our function slash limit, and so this is the following computation, and it appears that the number's approaching 1.6667, and so what's happening is it forms a fraction 1 over 6. That's how it looks like on our graph. And so then we end up getting a limit. So let me write it out right here. We get the limit of the function f of x equals the square root of t squared plus 9 minus 3 divided by t squared approaches 0 is equal to 1 over 6. So that's how we say it. Alright, so what is this all about over here? Zoom in your calculator. So let's say I kept plugging in numbers smaller and smaller into my calculator. Let's say I plugged in 0.000001 into my calculator. What do you think that'll give me? That'll give me 0. And so then we end up getting a graph that looks like this when you zoom in on it. It looks like it's touching 0. But this is wrong. You don't want to do that. That's wrong. And you're going to learn in this chapter why sometimes using a calculator and stuff could give you the wrong answer. So, especially for limits. Alright, so example 3. Guess the value of the limit of the function f of x, which equals sine x divided by x as x approaches 0. Alright, so we gotta do the same thing we did with the other examples. We plug in numbers into a graph such calculator. I know that sometimes the graph gives you the wrong answer and stuff, but for the sake of this section and chapter, that's what we had to do. And it's a valuable lesson because it teaches us that a calculator is just a tool. You know, who made the calculator? People made calculators. So I mean, they're not gonna always be right. Alright, anyways, so we plug in a number. Let's say we plug in the number 1. It equals 0.841478. And we can't plug in 0, right? Because we plug in 0, it's going to be undefined. And at least that's what it's going to tell us. And so we plug in a bunch of numbers close to 0. So let's say I plug in 0.001. I'm going to get 0.999, etc. And so it looks like when x is approaching a, right, or 0 in this case, it looks like it's going to give us 1. And so we're going to have to say the limit of the function f of x, which equals sine x divided by x as x approaches 0, is equal to 1. Alright, example 4, investigate. So we have the limit of the function f of x sine pi divided by x as x approaches 0. Alright, so this is going to be an interesting problem. So we plug in numbers into our given function. So I'm just going to give you some of the numbers. So let's say you plug in 1 into this. What does it give us? So you know what happens when sine is pi. And trigonometry will give us 0. Alright, so it gives us this assumption that this is going to equal 0. But if you see the graph over here, it definitely is not giving us 0. And so let's say we're approaching 0, right? Let's say we give it another number. Let's say we give, I don't know, 0.1. That's going to give us sine 10 pi. And so we know that if this is anything to do with pi, right here, you know our trigonometric functions and stuff, so we know that this is going to give us 0. So, and let's just say we started plugging fractions like this, 2 over 5. And so something like this you might want to plug in your calculator, you know. But let's say you did 2 over 5. That ends up giving us 1. So I want you to take note of that this gives us 1. And so now it doesn't appear as if our given limit is approaching 0. It looks like it's approaching 1. But then I plug in this next number. I say 2 over 103, you know, because for the sake of showing you big numbers. Then, what do I get? Well, if you haven't plugged it into your calculator already, you'll be able to see -1. Right? So if you plug that into your calculator, you'll be able to tell that's -1. And so there's something that's happening. The values of sine pi divided by x is oscillating between 1 and -1. And so if you look at our graph over here, so this is why the graph looks all weird. It's because what's happening is that these numbers are changing by just a little bit, and they're going 1, 0, -1, 0, 1, 0, -1. So they're going back and forth. And since the values of this given function do not approach a fixed number as x approaches 0, then we have to say that the limit of this function, f of x, sine pi of x as x approaches 0, and you guys could guess it, does not exist. Right? Because there's no fixed destination. Alright, so example 5. Find the limit of the function f of x, which equals x cubed plus cosine 5x divided by 10,000 as x approaches 0. Alright, so this is an interesting one. Alright, so let's say we gotta do the same thing we've been doing, which is using this calculator and table to plug in values, right? So we plug in some values for our function. So let me just put f of x. So I'll write it all out. And so let's say we put 1. It's going to be 1.000 something. Don't want to worry about that. Alright, so we go down, we keep plugging numbers, And what we're trying to do, we're trying to approach 0. So let's say I put 0.01. And so what this function is going to give us, it's going to give us 0, 0, 0, 1, 0, 1. And so it appears that this function is approaching 0, right? No. If we kept plugging in numbers, so let's say we plug in 0.001, and let's say we keep going, it's going to end up giving us 1 divided by 10,000. Alright, and so what's happening is that no matter what number we put in, we keep putting numbers in, it's going to be approximately 1 divided by 10,000. It's crazy, huh? That it looks like it's approaching 0, but it actually approaches this number. And so this is a valuable lesson for us. It's easy for us to guess the wrong value when using calculators. And this is really not really trustworthy, you know? But at the same time, we're not going to do it by hand and by your head, right? Because that takes too long. And so later in the future, we're going to develop foolproof methods for calculating limits. And so what that means is we're going to develop ideas that allow us to get to this number right here, right? This number right here, without having to plug in so many different kinds of numbers into our function and guess, because guessing just takes too much time. And so we learned the derivatives. We're going to learn that in a couple of chapters. Alright, one-sided limits. The heap-side function h is defined by h of t, which equals 0 if t is less than 0, 1 if t is greater than or equal to 0. This function is named after the electrical engineer Oliver Heaviside and can be used to describe an electrical current that is switched on at time t equals 0. As t approaches 0 from the left, so it's the left hand side, it approaches 0. And as t approaches 0 from the right hand side, it approaches 1. So 1, 0. There is no single number that ht approaches as t approaches 0. Therefore, the limit t, ht does not exist. So the limit does not exist. We notice as ht approaches 0, as t approaches 0 from the left, and as ht approaches 1, as t approaches from the right hand side, we indicate that this situation symbolically by writing. And so this is pretty important because we learn what it means to have a left hand side of a limit and what it means to have a right side of a limit. So this means this little negative sign that looks like on top, a little dash you could say, means going from the left hand side. And so that will be equal to, if it's coming from the left, what it's going to equal to? 0, right? And so what happens if our limit t approaches from the right side? It's going to look like this, symbolically, plus sign. And so what is that equal to? The solid dot right here, which is 1. So that's what these limits approach from each side. And what happens if our limit, we want to find the limit like this? Like I said earlier, that it does not exist. Definition of one-sided limits. Alright, so right here we have it symbolically. which means, what does this mean again? Left hand side. What does this mean? Right hand side, right? And so, which says the left hand limit of the function f of x as x approaches a is equal to L. If we can make the values of f of x arbitrarily close to a successfully by taking x to be sufficiently close to a with x less than a. And so all that really means is just that this will be approaching to the left. So that's all I was saying. And this is just saying it's going to be approaching to the right. Alright, so this is a pretty important mathematical statement for the limits. And what it means symbolically is saying that if this limit, if and only if the limit from the left and the limit from the right hand side are approaching the middle, or are approaching a certain given value for a, then this limit exists, right? This limit is not defined if the left hand side and the right hand side are not meeting up together. So that's basically what it's saying. Alright, the graph of the function g is shown as following. Use it to state the values if they exist of the following. So we got all these limits right here. Alright, the limit of g of x as x approaches 2 from the left hand side. So let's see what's happening on the left hand side. So we're going that way, right? It looks like it approaches 3. So that's our answer. Alright, let's look at this next limit. It says as it approaching 2 from the right hand side. So it's going this way. Alright. So what do you think it is? It's going to be 2. Alright. And so here's the big question. What happens if, is this defined or not? This is basically what this question limit is asking us. It says the limit of g of x as x approaches 2. And so we take a look at this. And since the left and the right limits are different, we conclude that the limit of g of x, the function g of x, approaching x plus 2 does not exist. So DNE, that means does not exist. Alright, so this one, let's see it. Limit g of x as x approaches 5 from the left hand side. Let's see, so this is our left hand side. It looks like it approaches, what does that look like? 2. And from the right hand side, what does it look like it approaches? 2. Alright, and now the big question. It says this time the left and the right limits are the same, and so by our definition, you remember our definition was if the limit approaches from the left and the right hand side, then the limit exists. Therefore, it equals 2. And even though it's open, we have open circle right here, open point. Despite that fact, we take notice that g of 5 does not equal 2. Right, so it equals 1. But it appears from going from the left and the right hand side, it will equal 2. So just take note of that. That we know that so this was the same. We know that g5 is not equal to. So we know that for the given point, it does not equal 2. But for the limit, it equals 2. Alright, infinite limits. Find the limit as the function of f of x 1 divided by x squared approaches 0. So let's see what happens if it exists. Alright, so we gotta keep doing what we've been doing, which is using a calculator and a tables of values. And so we have x, we have our function, so let's plug in some numbers. So let's say we plug in 1. And we plug in 1 x squared. It's going to be 1 times 1, which equals 1. Let's say we plug in negative 1. Negative 1 times negative 1 is 1. 1 plus 1, it gives us 1. You know everything that's squared is positive. So this would be 1. But let's say we kept plugging in numbers, right? And we're trying to get close to 0. Let's say we plug in 0.001. What number does that give us? If you plugged it in, you'll know that gives us 1,000,000. And so the values of f of x can be made arbitrarily large by taking x close enough to 0. Thus the values of f of x does not approach a number. So limit x that approaches 0 for 1 divided by x squared does not exist. So this limit does not exist. But there's a better way to say this. So there's a better way to say it does not exist. To indicate this kind of behavior exhibited, we use the notation of, so we write our limit again. So what do you think notation we use? We say that this limit equals infinity. This does not mean that we are regarding infinity as a number, nor does it mean that the limit exists, right? Because the limit still does not exist. As if that this is a better way to define it. It simply expresses this particular way in which the limit does not exist. And so 1 divided by x squared can be made as large as we like by taking x close enough to 0. And if you guys didn't plug it into your graph and your graphing calculator, right? This is how our given function such limit looks like. And so as we're approaching from positive or negative to 0, it's going up. And that's why we got this big number, 1,000,000. Alright, definition of an infinite limit. Let f be a function and defined on both sides of a, except possibly at a itself. Then the notation right here would be, say, the value of x of f of x can be made arbitrarily large, right here, by taking x, so this is x, sufficiently close to a, but not equal to a. So that's what this is saying. And so we could say that a lot of different ways. So here's other ways we could say this. F of x approaches infinity as x approaches a. So the limit of f of x as x approaches a, x is infinity. F of x becomes infinite as x approaches a. F of x increases without bound as x approaches a. And so you might read a problem and might say this, or you later on in mathematics you might learn different ways of saying this, but it all means the same thing. Alright, so right here, now we have our definition of an infinite limit, but for a negative infinity. And so it says, let f be a function defined on both sides of a, except possibly at a itself. Then, so like the other definition, except now we're going to have negative. And so let's read this expression over here. It says, the values of f of x can be made arbitrarily large, negative by taking x sufficiently close to a, but not equal to a. So the only difference is that we're going to have something that says negative. Alright, so let's take a look over here. And so right here we have an example of how negative infinity looks like. So it says another notation. F of x approaches negative infinity as x approaches a. Other expressions. And so it will be the same expressions, except now we're going to have negative. And let's say this one down here, it says decreases instead of increases without bound. So that's just the difference. Alright, definition. The vertical line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. And so these are all mathematical statements. And while these mathematical statements are saying infinity, right? So this says that infinity just for both left and right. This says infinity from the left, infinity from the right, negative infinity. And so where would our asymptote be for over here if we have y equals 1 divided by x squared? It would be, if you guessed it, in the center of the y-axis. And so this is all that this is saying. It says the vertical line x equals a is called a vertical asymptote of the curve y equals the function of x if at least one of the following statements is true. And this is true, right? Because this is going to infinitely up the y-axis. So that's where the asymptote's at. And that's where the curve's approaching infinity. Alright, find a limit for this function as x approaches 3 from the right hand side. This one says find the limit of the function as x approaches from the left hand side. And so if we were to take a look at our graph, so let's say we plugged in some points into a table of values, and like I said, we've been using our graph for this section for a while, so we know we had to do that. It appears it is going infinitely, right? And over here too. And so what number is this approaching? Let's see. So let's try this problem first. And this is saying from the right hand side. So if we plug in a number relatively close to 3 for our limit x approaching 3 from the left hand side, then we will get, so let's see. So let's plug in x equals 3.01 for this function, right? Because this is our function on top and on the bottom too. So let's see. This is our function. Let's plug in 3.01. So then we end up with 2 times 3.01 divided by 3.01 minus 3. So what is this going to equal to? So if you had a calculator, you could just plug it in. If you don't, it's pretty easy to work it out by hand. So it would be 6.02 minus 3.01. If we take this, we move it, so that's one method, right? Instead of just dividing, it ends up giving us 602. So we get 602. So from the right hand side, right, because this is what it says, it appears as approaching infinity. So we could put equals infinity. Doesn't mean that this exists, right? Doesn't mean that this exists, it just means that it approaches infinity. And so likewise, if we plug in a number relatively close for this part of our example, let's say we plug in, I don't know, 2.99, right? Because that's relatively close to that side of the problem. So let's say over here, it's going to be 2 times 2.99. If you're ahead of me, you could work out the problem. We know that's going to be the bottom part's going to be negative, so that's going to equal, what do you think it equals? Negative 0.01. On the top it's going to be 5.98. And like we did over here, we could move the decimal places. Divided by -1. And that ends up giving us negative 598. And so it looks like from the left hand side it's approaching infinity too. And it appears that at x equals 3, which is 3, that we have a vertical asymptote. So keep that in mind. Example 10. Find the vertical asymptote of the function equals tangent x. Alright, so what do we know about tangent? Especially if you take in trigonometry. If you haven't, it's okay. I don't condemn anybody for not learning calculus is hard when you don't know a lot, but I'm trying to teach my course so anyone can learn it. So let's say that sine x, this will be cosine of x. So if you take in trigonometry, we know that this tangent equals this. So that's really important. It says note when x equals 0. So what happens when x equals 0? This whole entire function equals 0, right? So if you have a calculator on hand, you don't even need to know trigonometry to know this. So let's plug in tangent equals 0, like it's a 0. Alright, so what happens if we start plugging in numbers like pi and a half? Let's see what happens. So with this, let's see, I plug in tangent pi divided by half. It says error. It says error. Right. So we know that, right? So we gotta figure out potential vertical asymptotes. And so what do you think it's going to give us vertical asymptotes? We gotta think of numbers in which cosine is 0. So what number did I tell you guys to plug in your calculator? Pi and a half. So what happens when cosine's pi and a half? If you take in trigonometry. So cosine's, what did I say? Pi and a half. So this is 0. That's pi and a half. That's pi. We know that when cosine's pi and a half, it's 0. Because cosine, big significance is x, right? So if cosine was 0, it would be 1, but since cosine's pi and a half, it's 0. And so that means that when this is 0, tangent is undefined per se. But what's happening is when cosine's undefined, our curve, or the tangent line, it's going infinitely up. So we gotta figure out more points where cosine is 0. So what other places is cosine 0? 3 pi and a half. Alright, what else? Negative pi and a half, right? Negative numbers too. And negative 3 pi and a half. And so there's a trend happening. Alright, this question's asking us, remember what the question's asking us, it says, find the vertical asymptote of this given function. And we could tell there's an infinitely many of asymptotes. And so how would we write this out if we know that these functions are approaching from the left hand side and the right hand side are going infinitely up, down, and we have infinitely many asymptotes? Well, then we have to write something out like this. We say thus x equals pi and a half, right? Because that's a significant number that matters when tangent is an error and when cosine is 0. So this is really important. Plus n. Why n? Because n signifies that this is going to change for a given asymptote. And pi, right? Because how long does it take for us to change over here? That's a pi, 1 whole pi. Right? 1 pi takes us to change from over here to over there. It gives us another asymptote. Alright. But what happens if we had a certain number right here that's not leading over there to 3 pi and a half? Let's say we had 0.1. Well, then this would be wrong, right? So now we gotta keep adding to it. So let's say when n is an integer. So what does it mean to be an integer? An integer, right? It means to be a whole number. Right, we can't put 0.5, 0.1, 0.2, because then we're doing what the function is already doing. It's going infinitely up and infinitely down, etc. It has a bunch of points in here for its function, its curve. But we want to do what this question is asking us, right? We want to find these asymptotes, so we need integers, so whole numbers, not fractions. So this is our statement. X equals pi and a half plus n pi when n is an integer. If you like this video, please like the video and subscribe to my channel. It would mean a lot and it will help me to keep making videos like this for you and everyone to watch. If you have any questions or comments, leave them down below. And if you are confused, please leave a comment down below. And in the next couple of days, I will make more videos explaining limits. Thank you guys, and I can't wait to see you all next time.